All right, that should be fine. All right, look, tutorials can be boring, especially for the people who give tutorials. So when I do it, I try not to bore you, and the way that I do it is I write a new tutorial about the things that I'm interested in, because I'm pretty sure I won't be bored. I hope you won't be bored. So in order to try and maximize the chance that you won't be bored, please ask questions, okay? Please tell me what you don't understand or what you are puzzled by or what you want, okay? Because if you don't, then I'm just going to go on with what I like, and it may not be what you like, okay? So you have some small discretion in the talk. Oh, yeah. Oh, you can't do that. Ah, jeez, I hate this thing. Okay, so I have my own personal view about computational science. Don't believe anyone. It's all BS, right? Until you can run it. People publish a lot of papers, and it's crap. And if I can't run it, I don't believe absolutely anything. And that's what I do when I review papers. I say, look, if I can't get this, I don't care what you said. It's the same as an experimental discipline where if I can't titrate your solution, I don't care, right? And you shouldn't. And I think we have to develop this kind of discipline in computational science where if people don't have open source software, if they don't include directions for running it, they should not be believed. Don't believe anything I say unless you can run it on your own machine, okay? And I think you'll find that you can. So what I want to do is, I want to do not a brief, but a somewhat short introduction to running PETSc, because if you can't run PETSc on your laptop by the time I'm done talking, I haven't done my job. Okay, it's really simple. It's very, very simple. You download the tarball, you configure, you make, it's done. And if you can do that, then the next thing I want to talk about is how to do something meaningful. Okay, I want to talk about running a somewhat sophisticated Stokes example. The reason is that a lot of times when we do tutorials, we talk about here's a vector, here's a matrix. I can't get excited about a vector and a matrix, really. I mean, yeah, I mean, linear algebra underlies everything we do. But honestly, if you can do your job with a vector and a matrix, probably not that interesting. So let's do something that really matters for science. We can do science with the Stokes problem. We can do mantle convection. We can do incompressible flow. We can do paint going over an obstacle. I mean, there's lots of things we can do. So let's do the easy stuff first. Look, what is PETSc? I'm serious. Tell me if you don't understand. Tell me if the example that I said doesn't work. Tell me if you want to see a picture. And this is the most important. Mail this. We're there 24 hours a day, and everyone there likes to answer questions. It makes them happy. So mail your questions. Again, tell me your questions. It really, really helps. Okay, look, what can we do for you? The point of having people help is not that they can solve the problem, it's that they can guide your decisions. When you do scientific software, if the person driving the science is not in charge of the code, it will never be successful. It will be a solution looking for a problem. It always has to be the person in charge of the science driving the code. What we can do is we can guide you so that you don't make a bad design decision that prevents you from running on the largest machines. It's always a preventative thing. These algorithms tend to naturally scale. We just want to prevent you from doing things like I'd like the whole matrix on every process so I can set a boundary condition. You don't want to do that. And sometimes people really think that's the right way to go. All right. And also, look, PETSc is not something like Abacus or Dyna 3D. It's not an app that you can run to solve a certain problem. It's a set of libraries. You have to have a problem in mind. You want help on solving it scalably. That's what we can provide. And it's for experimenting. And let me tell you, there is no way to know what discretization and what solver are right for your problem up front. And there are many papers to this effect. I can cite some, but just believe me when I tell you that the ability to change solvers and to change discretizations is very valuable because you can compare these things. Okay, that's why that's up there. Okay, and this is what Barry says. So this guy is the guy that started PETSc, and he's a real genius. I was very surprised when I went to work for him because it's authentic. You know, he knows what he's doing. And it's hard. And the reason it's hard is because we don't completely understand it. Look at linear algebra. We completely understand linear algebra, and therefore the interface has been fixed for almost 25 years. So Scalapack has a linear algebra interface. It's very, very similar to PETSc. It's very, very similar to Trilinos. So that's why I don't want to talk at all about the linear algebra interface, because everyone knows it and everyone agrees, okay? And the problem is that if that's what we wanted to do, it would be perfect. But we don't want to do that. We want to do non-trivial PDE solvers. And if you want to do that, you have to venture into territory where no one agrees. What discretization? No one agrees. How does the discretization interact with the geometry, interact with the solver? No one agrees. So I'm going to give you my idea of how that should happen, okay? And this is actually really cool. This is something from Bill Gropp, who was the co-creator of PETSc and also created MPI. And the idea is, look, you have to look from the top, okay? You can't mess around with details until you understand where you are going. And so I want to try to look from the top and tell you guys how this might work. And PETSc, look, you can download it freely. You can make a company that sells PETSc, no problem for us, okay? We don't care because you're not going to beat us. You know, you're not going to come out with stuff faster than we do. It's not going to happen. And whatever language you want, if there's a language up there that you use that we don't have, just tell us. And it runs on everything. It runs on my iPhone because Barry is crazy and has everything running under Xcode. So you can run the example that has driven cavity on your iPhone. Get a picture. And there's an example. It's not many people. So at any given time, we're about 4 or 5 people. Lissandro is the guy that does everything in Python, and he's amazing. And if you've ever heard of Cython, he's almost solely responsible for that. This is us. You can tell that the longer you're in the project, the more pixelated you get. And it's used for a lot of stuff. So yesterday you heard him talk about Stomp. There's also pflowtran. Fluidity, OpenFOAM, OpenFVM. There's a lot of stuff that uses PETSc. And I think the reason that it is used is that it's very easy to integrate into your project. And I sometimes talk about how to integrate it into a project. I don't want to talk about that today. I want to talk about solving non-trivial problems. So this is just to let you know that it's not BS. We can run on huge machines. We can get nice numbers. How many people run on over 50,000 cores as a matter of course? I thought so. Look, it's great to talk about, but most people run on their laptop or their local cluster that they can control. And what I'm telling you is, the idea here is that we know that you run on your laptop or your local cluster every day. And what we're saying is, take that code and put it on the biggest machine that you want, and it will run pretty well. The idea is that you don't have to change. You write one code and it works, okay? And it's a little bit more of a step. It is not MATLAB. There is a learning curve. But if you take that step, if you make your code run on your laptop, it will run on the largest machine that we have today, and it will be okay. And if you tweak it a little bit, it'll be great. And I'm just going to show you stuff that we've done. We've done dynamic rupture and earthquakes, where we can accommodate triangular meshes, hex meshes. We've done magma migration, which is very complicated. It's actually a Darcy-Stokes problem. It's got, 5 different equations. It's a cool multi-physics. And you could get stuff like fingering feedback. So it's neat. We can do fracture mechanics, which is actually a variational problem. It uses tau that Jason's going to talk about later. It's very, very neat. It's an L1 formulation. And here it's in 3D. We can have cracks that bend around and stuff like that, which is very hard for the, say, XFEM people. I don't consider that real fracture mechanics. We can do very accurate things with vortices, say, for atmospheric dynamics or gravity. And we can do very difficult discretizations, say a discrete elastic viscous split thing for Oldroyd B. We can do it because we keep things simple. And this is like the coolest thing in the world. This is guys at Texas doing cancer operations on a dog real time while they solve the thermal problem, which I was blown away by. That's the coolest part of doing what we do, is seeing people do things that are amazing that you could have never thought of. All right, look, if you want to use Windows, I guess I respect you because you like pain. And so pay attention to these things, this link.exe. If you want MPI, you got to download it directly from mpitch. This is in there so you can go back to it if you have problems. We try to be as open as possible. Everything we do is immediately available on the web to you. We have a repository. You get minute-to-minute updates. The FreeBSD guys have us. The Debian guys have us. You can get a tarball if you don't like our, if you don't like our distributed version control. Who cares? Here's our repository. Everything in this talk that's magenta is a link. I think it's very important to put links in the talk. If you notice something that you wish you could click on and get information and I don't have it, tell me and I will change it so that it's linked. For instance, if I offhand make a remark like, oh, everyone knows that Kahoot and Shepard in 1988 had this result, you should tell me that's BS. You should put a link to the paper, right? So always, always, always get this stuff from the repository. When we do things, it's just a tag. Why do this? If you download a tarball, it's one thing. You build it, it's great. But you won't be able to easily get all the patches. if we fix a bug, you have to download a new tarball and rebuild everything. Here, if we fix a bug, you just pull to the latest tag. You just one line and it's done. So I highly encourage everyone to use version control. We have a configuration system. It's all Python because Shell is a horrible programming language. People who use Shell don't know any better, should be treated with care. Look, configure, what is the purpose? The purpose is to check that things will work before you try to build, because if you build and it breaks, it's difficult to untangle all the error messages. So we check that you have the right X. We check that you have the right BLAS library and MPI library and all these things. We also do a second thing that is more useful, and that's we download packages and build them for you. So suppose you want to do something like you're like, algebraic multigrid is what I really want. I would really like if you would download and build ML for me, which is going to be talked about. We do that. I'd really like if you would download and build Hyper for me, because I would love to try parallel ILU DT. We do that. And so the point of configure is twofold. It's to test and it's to automate this download of packages. And so, you know, you can easily reconfigure if you want to add something like, I just figured out I want a package. Well, you can execute this line and add the package, like download mumps, which is a very popular package because it's probably the best way to scalably solve a sparse linear system. And you can easily do it. You just add download mumps. In fact, I think I have an example. So I myself do finite elements, okay? And so when I do that, I download Triangle, which is a mesh generator in 2D. I download TetGen, which is a mesh generator in 3D. I do Chaco and Parmenides because I like both people and I don't want to weigh one over the other for mesh partitioning. And I have Scientific Python and Fiat, which is Rob Kirby's package for generating finite element tabulations. We download and install all this stuff. I myself think that, well, GPUs are incredibly hard to program and way overhyped. They actually provide a kick in performance of a factor 3 to 5, which is important. If you care about your result, it's important to run 3 times faster. 100 times faster is total bullshit, and people who say that should be locked up. But 3 is great, and we can do it. And so here, if you want to do it, is how I do. And these are the packages from NVIDIA. This does vector operations, and this does matrix operations. And if you don't want them, if you just want my finite element stuff that does assembly, you can do that, because sometimes they break, because they're not, NVIDIA is new to the library game, so they don't think that you on your, laptop with all your packages that you think ought to work together is that important. Sometimes it breaks. And you can do single precision. We can do all these packages. We can do all these kind of linear algebra packages and MPI, mesh partitioners, direct solvers, eigenvalue things, and FFT, and random number generators, and AMG, and time stepping, and mesh, and stuff. We care about the user experience. No one who was writing a pure package would do this, and I argued vigorously against doing this with Barry because it violates the encapsulation. It says, oh, I'm going to be responsible for this package, but he argued vehemently for it because it makes it easier on the user. Yeah?
It's a little bit of an aside.
Go ahead.
So if I was going to put this on unclassified network, so you don't have access to the internet.
Ah, great. Okay, how does it work? Fantastic. So here's how it works. suppose I wanted to download something like ML, which I got to be honest, I'm a big fan of ML because it just works a lot of the time, right? So this goes out on the network and downloads a tarball for ML. This goes and gets the ML tarball from wherever the hell it happens to be. Okay, so you can download it somewhere else, move it over to your classified network and use it, and it will automatically install. This you probably get from the PETSc FTP site. Okay, and it's FTP : www.anl.gov/mcs/ I can mail out the URL. But we definitely accommodate that kind of mode of operation because a lot of people that we work with work on either classified networks or networks for companies that are closed. And
documentation in your user guide?
yeah. Okay, building is really easy. We use Make. So we use CMake by default, and the CMake guys, I wish there was a CMake guy here so we could have a good discussion. I consider it to be pedantic and overly fraught and likely to break. So I use the Python version, but I wrote it, so I am partial to it. So use whatever you want. But so for instance, on Windows, CMake will build project files for Visual Studio. So I admit defeat there that they are better than me. But Python, on the other hand, will allow you to do things like code generation on the fly, which I use when I do finite elements, and I will show you when I'm running now, which I think is pretty cool. Yeah, all this stuff. So you guys will have these slides. So this is important, but it's not important to talk about. It's easy to add stuff. So if you want us to download another package, you can just call the reconfigure script. It will do exactly what you did before, and you add the package. That's the idea. We use our own stuff, so we get upset if it's hard. If I had to remember all the options that I just gave, I would be very angry. But you don't, because we write a script that remembers all the options that you just gave. And it should be easy to run examples. So if you want to run a nonlinear solver example, you can do it with Make. I do it with Python. It's similar. And you should be able to check immediately. This is what I did yesterday when I logged into Carver to make sure that everything was OK. And it was. Let's see. Oh, yeah, you can. And everything works with Python. There is a genius guy. His name is Lissandro Dulcin. And I wrote my own Python bindings to PETSc. It took me like a year. And I had to throw away everything that I did and hang my head in shame because Lissandro is so much better. And he is the guy that's single-handedly responsible for Cython, which, if you don't know, is the package that powers the bindings for global arrays and Trilinos and everything important because it's so much better than what everyone else did. And it's because Lissandro is so great. And so everything that PETSc does in Python and PETSc for Pi is due to him. And if you don't think it's amazing, think about this. PETSc does things like solve nonlinear equations. When you're solving nonlinear equations, what you do is you take in a function and you evaluate it as the residual. You don't know anything about this function. And Lissandro made it possible to write Python functions. You can have a Monte Carlo simulator written in Python and pass it into PETSc as the Python function, and we will solve that nonlinear equation. It's pretty freaking cool. And it didn't happen when I did it. It only happened when Lissandro did it. So I was blown away by that. No one cares about MPI. We try to be consistent. So a vector and a nonlinear solver and a matrix all respond to the view command. If you have view draw, it will try and draw a picture. If you do view draw here, it will draw a picture of the convergence. If you do view draw here, it will draw a picture of the sparsity, and I'll show you a picture of sparsity is coming up. All of these options are detailed when you give minus help. Yeah, I usually talk about this. I don't think it's important. I'm totally hot to get to actual code. Look, this is somewhat important. We have a manual. It is hundreds of pages long. I never read it because that's not the way I learn. The way I learn is to look at an example and break it down. And so this is really cool for me. Here's what we have. We have pages of examples. So we have maybe 300 examples. When you go to an example, it's an HTML upload. I wonder if I can get it on this screen. And every function call is hyperlinked to the documentation for the function call. I wonder, can I do it? Can I get it? I don't know. Is it? Oh, hold on. Yeah, no. I think I. Come on, you got to be kidding me. Oh, yeah. Hold on. Don't read my email. Oh, guess the count. Shoot. Oh, there we go. I have that. No, it's on my badge. Where's it? Oh, thanks. Okay, so let's see. 11, 3, 7, 2, 8. Because I really want to show you this, because I think that you guys will be impressed. C6, NI, UN, U0. Oh, come on. 11, 3, 7, 2, 8. Okay. P. Oh, thanks. Yep. PJ, C6, NI, UN, U0. Yes, okay. Come on, is that loading? All right, well, I'll keep talking while it's loading. Oh, come on. It's just not working, is it? Ah, there it is. Okay. So manual pages. Let's go to nonlinear solvers and SNES solve. And it's example 5 is my favorite. Okay, so look, we have the code all in HTML. And so you can scroll down and everything is hyperlinked and you say, I have no idea what this does. And it will take you to the manual page for that particular function. And it will also tell you where it's used. So this is how I learn things. There are people that push things into PETSc that don't talk to me first. It's annoying, but it happens. And so I have to figure out, just like you have to figure out what the hell their code does. This is how I do it. All right. The worst default ever. Did anyone think that a tiny little shrunken page was what they wanted? Okay, we also have a FAQ, and if you mail us here, we will respond 24 hours within 5 minutes, I guarantee you. Because we're embarrassed. We're embarrassed if we can't solve your problem. That is the best thing that could possibly happen to you, I think. And a lot of people just aren't. They just don't consider it their deal to solve your stupid little problem with your crappy configuration because you wanted to install this library, but we do. So look, I usually, at this point, talk about what vectors are and what matrices are, and I just could not bring myself to do it this morning because it's not interesting, okay? So let's talk about stuff that, that you can write a paper about. You could probably write a paper about this. You know, if you put an interesting rheology in here, you could definitely write a paper about that, okay? I didn't because I want to understand the results, but it's not hard. And that's the idea. That's what PETSc is about. Give you the tools to do something interesting right away. And so if you go to source SNES examples tutorials ex62.c, this is here. It's a Stokes on a square. Change it to use an interesting rheology. Example 31 is me doing this with temperature, trying to write a paper, actually. Example 30 is my much superior friend Rich Katz, who is a scientist, writing a paper. So, you know, there are a lot of good things there. I like finite elements. Look, if you like finite volumes, great. Finite difference, great. We support all this stuff. I want to talk about finite elements because I think it's under-supported by PETSc. Finite differences are easily supported. So finite elements, we write a weak form like that. There's a guy named Rob Kirby. He is at Baylor now, and he's great. And what he's written is a piece of software that can automatically, for any element you can think up, and I mean yell one out if you think it's not going to work, will tabulate the basis functions at quadrature points for it. And so here I run Rob Kirby's software to tabulate them for a bunch of different operators. It's cool, huh? And so this is how my example works. I run Rob's software to generate a C header file with tabulations of the basis functions at quadrature points. So I don't know what element I'm getting. I don't know what operator I'm getting until I get this header file, which is great because I can solve a whole variety of problems with the same PETSc code. So let's look at that. Here is how we think about objects. They have a creation. They might have an options prefix, which allows you to configure them from the command line, and I'll go into that further. And you know, they might have view and they have a destroy. Everything in PETSc is handles, so you can do assignment, you can do comparison. And if you're a nerd, like a programming nerd, this is the service locator pattern in Eric Gamma's book, or dependency injection. So this is, you know, common stuff. Everything can have a name, everything can have a type, everything can be set up and viewed. Don't put stuff in your code. Don't ever hard code the type of solver, or the type of preconditioner, or the matrix format, or how you're going to do parallelism. Never, never, never put that in your code, because that means you'll have to rebuild and change this crap every time you run, and it just doesn't make sense. So what we do is we configure everything dynamically. We say, create a solver, configure it from options, and run. You can tell it, use this file or that file. You can actually put everything you want in the API. If you disregard my admonition and want to configure it, you can do that. You can do it from an environment variable, however you want. I think this is really worthwhile because look, Noel Noctegal and Trefethen have a paper that says we took a whole range of linear solvers and every one was the best on a certain problem. There's a paper by Anne Greenbaum about GMRes, having any convergence curve on matrices, there are all these negative results that there's no way to tell which one is best. So in that scenario, the right thing to do is try everything. And that's what we want to do, try everything. And I think people just lie to themselves about finite elements. Is first order better than second order? Well, it's more accurate, but it's more expensive. Try both. And I'm going to show you trying both. Yes?
Is there an easy automated way to do options, sweeps, and parametric studies?
Yes, for. There's a for loop in Shell or Python or anything you want. You can do that. And that's what we do. So never, never, never code up a linear problem. No one cares about them, I think. Does anyone just solve a linear problem here? I won't vilify you. Just tell me. I think almost everyone says, well, I kind of have a linear problem, but I have some nonlinear parts. The thing is that in PETSc, if you have a nonlinear solver, it's just about as good as a linear solver. There's no overhead if you give the right options. Just don't do any norms. Don't do any checking. You can make it a linear problem. And then when it's nonlinear, you just slowly turn stuff on without changing your code, which is the way to write maintainable code. Now, my friend Jed tells me that what I should actually do is always make stuff a time-dependent problem and just go back to the steady state if I don't need it. Same idea. And so you might be thinking to yourself, didn't time integration suck in PETSc? Honestly, yes, it did. It was terrible. But these smart people rewrote it. Jed and Emil Constantinescu and Peter rewrote it. And every time something's in magenta, it means it's a link. So this is a link to these guys' home pages so you know who they are. And the time stepping in PETSc is now pretty impressive. Here's what we do. We have this implicit form where G is everything you want done implicitly, F is everything you want done explicitly. So if you have an explicit problem, just give F. If you have an implicit problem, just give G. If you want semi-implicit, give both. Great. And here it is. Give the residual, give the Jacobian implicitly. Give the right-hand side. We have lots of crap. We have this stable stuff from Dave Ketchison, right? That's very low memory. We have this stuff which is very accurate. Dense output. What this means is that you can get interpolated output in the middle of time steps. I think it's a lame way of saying it, but that's what the people in the community say. We have Rosenbrock W. We have semi-implicit. What was embarrassing is now, I think, a great strength. And I think if you have time-dependent problems, you should really check this out. Here is stuff that I don't even understand about, stability estimates and everything that Jed wrote because he implemented this all. I think it's very impressive, though, that we can do DAEs and all this stuff. So this is all available to you easily. Yeah. Yeah. So we'll see. I'll be interested to see if we can't do something that Carol talks about. Is she here? Where's Carol? These people in town never show up, right? They come right for their talk. So if you don't believe me, and if you were listening, you would not believe me, right? You would say, this is crap. But run it for yourself. And so here are some 1D examples. And, that 1D, I agree, no one's going to publish a paper about this. But well, you might if you're biology, because there are some interesting 1D problems in biology. You can test these solvers, like this SSP solver. And if you just give these options, you can run this. This is what I trust when I can run something. If you're not running it now, you don't care. Honestly, for me, I would be running it now. I don't solve a lot of time-stepping problems, but I solve a lot of nonlinear problems. And what typically was the case is people run Picard or they run Newton. Okay, this is such a desert here of options. There's a lot more in the universe than Picard and Newton. There's semi-smooth methods. So for instance, if you have positivity constraints like concentrations that can't go below 0 or something like that, we have methods for that. Quasi-Newton, we have that. Nonlinear GMRes, nonlinear CG, nonlinear SOR, Gauss-Seidel, the nonlinear multigrid. We can do all of this, and you can compose them. Let me give you the coolest example, I think, of doing this. We have a stochastic PDE, okay? And the stochastic PDE had a really crap Jacobian. Why? Well, we weren't willing to pay enough to calculate a great Jacobian. We just differentiated what we got, which obviously was bad because we had these non-smooth paths. So we got a crap Jacobian. So, you know, you could cry a little, but how are we going to solve the nonlinear problem? Well, you can do Picard. You can just substitute in and substitute in. It takes forever. You can try to do Newton, but the Jacobian's not great, right? What do? What we did is we said, we're going to use nonlinear GMRes as a preconditioner for Newton. And that works great because what it does is smooths over the rough spots in this inexact Jacobian. And we were able to solve it. It's a problem in nuclear damage of materials, which I will show you later. And so we can help you solve hard nonlinear problems. And I just wanted to put this in because I drew this myself with ticks, and I thought it was sweet. The blue stuff is kind of new. It's stuff we're just working on. And so if you see anything that you want me to talk about, tell me. Because I'm going to talk about what I think is interesting right now. But if you tell me, I will go to something else. Look, the most important thing I think I can tell you is the way to write simulation code. So this is what I want to go over. I took this directly out of example 62. So you can go back, look at the example, see what I'm talking about. And I have, Hans-Peter Langenthal just has another publication from Springer about the Encyclopedia of Programming Languages. And I wrote an article on how programming languages impact numerical computation, okay? And what I want to say is what I'm going to say on one slide. Look, what we do is we create something, it's an opaque handle, we configure it from the command line, and we solve something. This is fundamentally different from what some people do, which is they would say, create Newton. You would, and even Trilinos, I disagree with the way that they do things, and that's because they create type names in your code that you don't give a crap about. They would say something like nonlinear solver template Newton. I don't care if it's templated, it's still a type name in your code that doesn't need to be there. And you say linear solver GMRes. It created a type name in your code that doesn't need to be there. And I didn't want to show code examples of theirs because they're going to talk later, but challenge them and say, look, what is this? Why do I want to set this when I don't have to? We don't make you set it up front. You can change the type of anything dynamically. You can say, well, I kind of want GMRes, but then I want to try BiCG and all this stuff. And that's the way this should function. You should never, ever, ever recompile. All configuration be dynamic. I don't deny that factories is how everything works. Trilinos uses factories. I agree with that. Yeah, they're right. But you should not see them. The user should not see them. I'm going to take away, you notice that I have all the error checking in here. Always write code with error checking, but I'm not going to show it to you in my examples because it takes up space. Now look, what if we do something like this? Nonlinear solver, nonlinear GMRes, set the restart type. Okay. Suppose I don't use nonlinear GMRes. What happens? Well, this just gets ignored. What happens in C++ if I want to do this? Well, first I got to do a downcast, which is horrible. Then I got to check that that didn't blow up. Then I got to use the downcasted thing to do something. So that's like 5 lines, and it's ugly, and no one wants to see that. And what we do is we hide all that kind of stuff from you. Okay? And I think that, personally, for me, that's better. Although I would never do this in my code, I would do it from the command line. But you can do it. So for instance, and we namespace everything. So if you want to do stuff from the command line, of course, you have to disambiguate stuff. So you can give any kind of namespace that you want. So for instance, Stokes, we could give quasi-Newton, and this would be ignored. When you are solving a problem, all we need from you is the ability to form a residual. So if you want to be in control of everything, you just give me a function that forms a residual, and you're done. So f of u equals 0 is the problem you want to solve. We will do, you handle everything. You handle parallel communication. You handle geometry. Fine. Okay? Now, if you want some more help, you have to obey more of our rules. If you don't, fine, we can do this. You know, we can use all of your stuff. But if you want more help, here's what we do. If you want more help, you have to describe more about your problem. Now, the easiest thing to describe is how your problem is set up in parallel. You can say, well, I don't want to tell you anything about my mesh. I don't want to tell you anything about my discretization, but I will tell you how my stuff is broken up on processors. Fine. Then we'll allow you to compute locally, and then we'll assemble the full Jacobian. We'll allow you to run a full space method. This should be communicated to the climate people because they don't form full residuals, and it's embarrassing, in my opinion. The global Earth model just, tosses stuff back and forth in a Schwartz type way between atmosphere and ocean, and it's terrible. They get a lot of money too. And we don't make you set a Jacobian. We can calculate a Jacobian from finite differences, Jacobian, free, Newton, Krylov, if you want. But if you want to specify it, here's what you do. And if you look at example 62, I calculate an exact Jacobian as a matrix because that makes it easier to precondition, but I can also do it matrix free if you want. If you listen to my friend Jed, he will tell you that matrix free is the only way to go because it's the only thing that will run on modern architectures. How he's going to precondition that, it's unclear. Probably Chebyshev, which works for some problems. So, you should listen to him because he is a smart dude. What is a DM? Okay, the DM, I think it stands for data management, but Barry refuses to weigh in on this, even though he made up the name. It can create local and global vectors. So what we do is for every kind of data layout, there is a DM. There's a DM that just says, I know how stuff is partitioned. There's a DM that says, oh, I know about structured grids. There's a DM, I know about unstructured grids. And this is very similar to the conceptual interface in Hyper. So I give them credit. They did a pretty good job there, knowing that you needed this part. And we were afterwards. You can always reset the type of things, like the type of nonlinear solver, quasi-Newton, Newton, whatever you want. You can set a nonlinear preconditioner, which I think we're the only package in the world that can do this correctly. Tell me if I'm wrong. You can set, tolerances and monitors and stuff. And I'll show you that in the hands-on, we'll just run stuff. That's what I like to do. I don't believe anything you can't run. So I want to give you an idea of what is possible. Okay, this is the coolest thing I've ever seen from the command line, and it was done by my boss, Barry Smith, because he is a little crazy. Okay, AllenCon, what is it? AllenCon is about, they're using that to model radiation damage to a material. So Cahn-Hilliard is used to describe the aggregation of domains, and AllenCon is used to describe the diffusion of damage, right? So it's first order triangular elements, constant mobility, and you can do this. So what's happening here? On the outside, you can run flexible GMRes with 5 levels of structured multigrid, okay? So you can do this. This works with any solver if you are willing to do structured grid things. I'll show you unstructured later. We do Galerkin. We know there's a null space here, and you don't have to worry about a null space on the coarse grid. So for instance, I solve a problem that looks like this. This is a downgoing slab. This is it's that. This is a downgoing slab. This is the mantle. This is the crust. I solve this, and there are weak constraints that implement the fault rheology here. So there's a null space because this thing can freely move because these constraints are weak. They're not strong in the formulation. And I can just use SVD at the coarse level and still use multigrid. So I think that's cool. We can get any smoother we want. And so right here, we have a constrained problem. We have a saddle point problem, okay? But we can still use a smoother that respects the saddle point. How? We use a sure complement smoother, which is easily done, and I'll show you in more detail how this happens later. And then we can use whatever solver we want for the sure complement and for the sure complement action. Yes?
What version is all this available in?
3.3. This all works in 3.3. It might work in 3.2, but yeah. So there are smarter people than us. One is in the back of the room, right? Okay, this is better than anything we could possibly do, so we just don't. We just use it, right? UmpPEC is better than what we could do too, and so we are all about using other people's software. Hyper, Trulinos, we use them because they work. We are interested in doing certain things, and the things we can't do, we will use whatever is the best thing out there. And we will not only use it, but we will automatically download it and build it and integrate it in it for you. And all these are automatically done. Because, yeah, we don't have that stuff. So I want to talk about something that most people don't have, that we have, that solves cool problems, and that is saddle point problems. Almost all people, well, not almost all people, lots of people have problems with constraints. Problems with constraints give rise to saddle point problems. This is a slide from my friend Jed, and his basic point here is, look, there seems to be this dichotomy between the way people solve these problems. Some people like to split it up, and this is what's called block solvers. And some people like to do this, and this is normally called segregated KKT smoothers for multigrid, okay? This is a false dichotomy. You can do all this from the command line in PETSc, so you can alternate. And that's our big point, is that we don't want you to have to choose in this arena. And so let me show you this stuff. Okay, what is field split? Field split has is analysis phase as synthesis phase. You tell me what is divided up. Okay, so let's do it. So what is Stokes? Stokes is elasticity, incompressibility, mass conservation. Okay? Now, I don't care if this is parallel, if this is on a bunch of processes. You don't have to have it stacked up any particular way. You can alternate however you want. But you just tell me what equations correspond to A and what correspond to B. That's it. And in finite elements, it's particularly easy because I can say, well, everything on the vertices is elasticity, and I have pressure on the faces, or something like that, right? And so I can easily describe this kind of split. Once you have this split up, you can do all the combinations, additive, multiplicative, Schur complements, anything you want. And you can do it inside multigrid. So let's take a look. You can split up, once you have defined these fields, you can have, so for instance, magma dynamics has 5 fields. It has a solid velocity, liquid velocity, the shared pressure, in components. And so we can combine any of the fields together that we want and make a split. So for instance, if I had temperature in here, temperature probably couples to itself by diffusion, and it's present in the viscosity here, and let's see, Jed does this, so I think there's a thing here and thing here. And so we can choose to solve the temperature alone or solve it with the elastic part or anything you want from the command line. And we can say, well, we'd really like to solve this with Schur complement, or we'd really like to solve this multiplicatively. All of that is available for us. And I think I can, so let's take a look. Let's just do Stokes as an example. Go ahead.
But the way you are splitting, the boundary conditions are changing.
Okay, so good question. So how do you do it? There are at least two schools of thought on boundary conditions, right? One school of thought on boundary conditions is that you leave them in and you make an identity on the Jacobian and you put the boundary condition on the right-hand side, right? You can do that. I don't do that because I think it's cumbersome. So with two of my best friends, I have a piece of software called Pilot. Pilot solves dynamic and quasi-static rupture problems for earthquakes. We have this kind of a problem, but this is the double couple for transferring stress across the fault. And so it has the same kind of problem. We eliminate the boundary conditions by taking them, all of the constrained degrees of freedom, out of the system. And therefore, you don't have to worry about that. So that's the second way of handling them. It doesn't interact as well with active set optimization. Agreed. So we allow both in PETSc. You can do whatever you want. If it's just nonlinear solutions, I like eliminating them. So for instance, for the Stokes problem, we can say split the fields, combine them additively, do algebraic multigrid on the momentum, and Jacobi on the Schur complement. So you get a preconditioner like this. Here is 1988, someone thought of this, right? Now, you can actually do it better by putting the block triangular form, and Howard Ellman actually was able to publish a paper on this, because it wasn't obvious in 1994, right? You can, by changing the split type from additive to Schur, you can put an approximation to the Schur complement instead of just the identity there. And this is a good paper on that. And Olshansky actually proved strong bounds for this, for isoviscous Stokes. You can have different kinds of the factorization of the Schur complement here, lower, upper. You can do this least squares commutator form from the Andy Wathen. And in fact, you can do the full Schur complement factorization if you want. The beautiful thing about Schur complement factorization is the following. When you test things, you want the easiest thing to work. So normally you just say, LU this small problem and give me the exact result, right? But LU fails on a saddle point because you got zeros on the diagonal and you're like, what do I do? You can do this. You can do full Schur complement factorization on your saddle point problem. It will converge in one iterate. So I do this to test things. It better converge in one iterate. And you do LU on A. So let's do a real problem, right? If you download PETSc Dev, actually this works in 3.3. If you download 3.3, this bit of Python runs Rob Kirby's stuff so that we can get a P2 discretization of Laplacian and P1 discretization of the pressure. And then we can run just Jacobi. We can run block diagonal field split, so it's additive, right? And we run LU on the momentum and I on the pressure. Block triangular, change it to multiplicative. We can run a Schur complement. And this will run a full Schur complement, which will converge in one iterate. So we can check. And we can actually run multigrid with the Schur complement under it if we want. Although all of these examples are run on unstructured grid, and so I can't do it for you because it would require automatic coarsening of the grid, which is not ready yet. We have experiments, but I mean, honestly, it's not ready for prime time. So that is about field split. Let's see, how am I doing? What? An hour? Oh, okay. I went fast. So now I want to talk about what does the DM do? The DM is about telling the solver what is happening in the problem. It's our interface from the discretization and the problem to the solver. And this is the crucial aspect because it's very hard to get this interface right. And we've tried it many times, and I've tried it many times personally. And this is where everything fails. And why does it fail? It fails because you try to get too much information in the solver. If the solver knows that you do finite elements, for instance, then it'll break with finite volumes, or it'll break with a different element, or it'll break with someone who doesn't agree with the way that you do finite elements. Okay, so what we try to do is we try to break this coupling. We try to have the simplest description possible that goes into the solver in order to describe what's happening. So DM is our attempt to do that. So it encompasses too much. I think if you're honest with yourself, you would say, look, there's an awful lot of things going on here. Why don't you break it into a bunch of objects? I agree with that, but the problem is that we don't know what objects to break it into yet. So we just set them here. This is an experiment. I think it's a 6 or 7 year experiment at this point, but you have to be willing to accommodate these things if you want to get it right. So what does it do? Well, it does problem definition. So you tell it, I know how to calculate a residual. That's your whole problem, right? Your whole problem is I want to solve this guy. And so I say, I know how to calculate that, right? It's got to know how to discretize your problem, too. It also knows about how you partition in parallel, how you partition the fields, so that it can make vectors and matrices with the right partitioning and do things like global to local mappings. And it also has to know about hierarchy, so coarsening and refinement and interpolation. And we give you hooks so that you can do what you want for your resolution-dependent data. Okay, so this is my current understanding of the best way to do this. And I'm talking about it because I'm very interested in it. If you want to do staggered grid, I think some of the best options for complicated multiphysics is staggered grid discretizations, because they have unbelievable, powerful smoothers, Vanka smoothers for multigrid. They're very memory light and they're fast. Okay, so all of the finite element people can just go home crying, because staggered grid discretizations solve a lot of problems really well. And we gotta, if you love finite elements like me, you have to seriously question whether you would use them on some of these problems. And so, and in fact, even the best finite elements for Darcy-Stokes look like staggered grid finite difference. So this is stuff from Todd Arbogast at UT. And so how do you do this? And so we didn't support this previously. And the way we support it is with this object PETSc section. Now, I agree that the name might be a little forbidding. It's about being a section of a fiber bundle. But what is it really? What it really is it says, look, every piece of the domain, how many degrees of freedom are on it? So here you would say, well, every face, that's got 1 degree of freedom for pressure. And every vertex, well, that's got 3 degrees of freedom for velocity, let's say. And this is what the section does. We have an object called PETSc layout. And what that does is it's the traditional thing for a linear algebra guy. A linear algebra guy wants to know this. I have a vector. How is it chopped up, right? Okay. Totally understandable. You'd want to know that. What the section does is it makes that finer grained. It says, well, okay, you have a vector, and we don't want to chop it up by processes. We want to chop it up by points. We want to chop it up like vertex 0, vertex 1, edge 0. And so it's just a finer grain chopping up. So you can ask questions like the following. Give me all the degrees of freedom on this edge. Give me all the degrees of freedom on this vertex. Give me all the degrees of freedom in the closure of this cell. You can do that with this. And the nice thing is that it's only integers. It's only about mapping one integer to another, just like this is. This has size and an offset. That just has size and an offset. Boundary conditions are handled by it just like this. It's just size and an offset. Number of constraints, offset of the constraints. Easy. Fields, same thing. Size and offset for a given field. If I have Stokes, I'll show Stokes, so I'll go into it. Okay, look, this is great because linear algebra packages like PETSc only understand integers. Anything else, don't give me a class that encapsulates your element. It will fail. That will be a failure of design. Good design is robust. The robust way to do this is to give a list of integers to me. That's it. And it took me a long time to accept this. For years, I wrote class-based, object-based finite elements. It's a failure. All of it was a failure because the minute you change something, it broke. This doesn't break. This says, just give me a list of the guys that are in a certain field or a list of the guys that are on a certain point. It decouples the mesh from the discretization because I don't need to know how you got these degrees of freedom. I don't need to know the particulars of your element. I just need to know where they are. I don't need to know whether you're finite difference or finite volume or finite element. I just need to know how many degrees of freedom are where, and I can create vectors and matrices. I decouple the mesh from the solver. The solver doesn't need to know anything about the mesh. It just knows that I have one field here and another field here, and then I can do field split, and then I can do Schur complement, and I can do multiplicative, and I can do anything I want, and I don't need to know crap about what you're doing, which is great, because suppose that you have a code. Suppose that you have the bee's knees finite volume code, and I would never be able to understand how you're doing the limiting and everything like that. It doesn't matter, because you can just tell me, here is a list of one field and a list of the next field, and in one call, you can enable all of the field split preconditioners that I just said. That's the genius of it. I did this for my PhD. I got it all wrong. I had all of the objects in there, and it only worked with one thing, and it all got thrown out, and Barry went back and put it in this framework, which only deals with integers, and I was very upset for a while, but it turns out that this is much better. It also decouples the discretization from the solver, and this is kind of nice, because as I said, I use this discretization package, Fiat, and my solver has no idea that Fiat even exists, and it doesn't even matter that it doesn't know, because all I do is tell it the field division. So let's look at an example. So this is my high-level interface. So what I say is, oh, here's the spatial dimension. I have such and such fields. I have such and such components of each field. And this nummed off. So let's take a look. Suppose I want to do like P1, P0. How do I do it? In 2D, there's 2 degrees of freedom on each vertex, none on the edges, none on the faces, none on the cells. And for the pressures, there's none on the vertices, none on the edges, none on the faces, 1 on the cells. Okay? Q2, Q1, 2 on the vertices, 2 on the edges, 1 on the vertices here. Q2, P1 disk, right? Discontinuous. 2 on the vertices, 2 on the edges, 4 on the cells, right? Because it's P1 on a quadrilateral cell. You can do any discretization in these simple maps. This is how Fiat works. I think Kirby is a genius because he came up with this simple way of breaking down all these discretizations. If you pass this in here, then I can do layout for everything. I can do layout for coarse grids. I can do layout for fine grids. It commutes with the multigrid. It commutes with the field split. So I can do layout for any of the subfields because I know what's going on. And it's really simple. It's a list of integers that is very short. And this is how example 62 works. So example 62, I can do P2, P1, or P3, P1, or P5, P4 if I want. And Fiat supports all of these. And I can do RT0 combined with P0 or BDM or anything I want for an element. And all it does is make a header, and the header, the header has this particular array in it generated from Fiat. So in my opinion, beautiful. Okay, suppose you think that's crap. Suppose you think that that's not the way to do it. No problem, because we have a low-level interface. That high-level interface calls our low-level interface. What does it do? It says, okay, tell me how many fields you have. Tell me how many components. Tell me all of the entities you want me to know about. Right here it's cells and vertices. So I say, well, I have 3 degrees of freedom on every vertex. And they're for field 0, and then I have 1 degree of freedom on every cell, and it's for field 1. So suppose you have some layout that I would never, it's not finite elements, it's the discrete element, or some kind of thing that for explosions or something like that, that I have no idea about. No problem. You can use the low-level interface to just say, I'm going to tell you where all the degrees of freedom are, and it will work. And it's not very long, I think. So to do unstructured layouts, so we have a structured thing called DMDA. I'm not talking about it because I've talked about it for many years and I'm bored. So this is unstructured. DM complex means modeling with a CW complex. I understand that the name is sort of misleading, and Jed likes to call it DMplex, so maybe we'll change it. I can do any kind of mesh with this, simplicial, hex, hybrid, any kind of mesh. The reason is because it removes the unnecessary labels. I don't need to know the dimension of the mesh. I don't need to know the dimension of the components. I don't need to know the shape. It encodes all of them as a Haas diagram. And a Haas diagram is very simple. Suppose I have a very simple thing here with vertices and edges and a face. The edges all map to the face, and the vertices all map to the edges. You can encode any, even non-manifold, topological entity as a directed graph. And in fact, not only as a directed graph, but as a poset, because you can divide the entities into breadth first search levels in the graph. And that is why it's a poset. This is the right way to do things, because I don't need to say, these things are dimensioned blah, blah, blah. That's what's wrong with, oh God, what do they call it? ITAPs. That's what's wrong with the ITAPs interface. Don't use it. It's crap. And it's crap because they put a lot of unnecessary information in there. You can discover what dimension these are by doing breadth first search. You can discover that things are edges and faces and stuff like that, and you don't need to put it in your interface. And I think that is the right way to go, because it makes the interface very small. There's only a couple of functions, and I'll show you what they are. And I accept a lot of mesh generator input. So PyLith accepts Exodus 2 and Triangle and TetGen and Legrid and Qubit. I think these are great packages. I encourage the use of them. We don't do any kind of mesh generation, but we do mesh representation. The idea here is that you can get the mesh any way you want. All we have to do is understand it at some level for the solver, right? That's what we want. What's wrong with the way that packages are architected today? Let's take a package that I really like, that I respect, libmesh. Libmesh is a great package, okay? It enables people to do a lot of science. And what's wrong with libmesh is that they have a crappy integration with the solver, right? That is what we're trying to fix. And hopefully it will be fixed very soon, like in the next release of libmesh, they will respect this kind of stuff. They will deliver me this DM so that we can do field split and we can do domain partitioning and all this nice stuff that we want to do. And the reason is that they have all this information, but they don't know how to tell the solver about the information. So what they do is they make a vector and matrix, and it's this big monolithic thing, and then we have to discover what's going on. You don't want to do that. You want to tell people what you know ahead of time, but how do you do it? And so you do it by giving them lists of integers, I think. So if you look in example 62, it does the most sophisticated thing that happens is that it interacts. The one point where I need to know about the mesh and about the equations and about the solver is where I form the residual, right? When I'm calculating this guy. Why? I need to know that I am getting, say, the closure of an element. So how do I do it? Well, I have an operation for that. You say, tell me your DM, tell me your data layout, tell me where the values are stored, and tell me what part of it you want, and I will get it for you. And so how does it work? How does it work? Well, I just go back. I have this list of, for every point, I have a number of values, value 0, value 1, value 2. Okay, so I say, all right, what's the closure of F? Well, it's all the edges that f has, and it's all the vertices that those edges have. It's a transitive closure of the relation in the graph. Well, each one of these things can have some values on them. So I might have values on the face, I might have values on the edge, I might have values on the vertex. I stack up all these values, and I return them to you. Now, it's a little more complicated because things can have orientations. So I have to be careful about how I stack the values up. Barring that, it's simple. And this is what this does. It gives you a vector of all these stacked up values. And in form function local, what I do is I loop over all the cells. So I call the DM, I say, tell me what are the cells? And it says, well, everything from 3 to 17 is a cell. OK. Then I get the closure of every cell. And this is the input vector. So I get the finite element coefficients for every cell C, and I stack them up, and then I get rid of the space. And then I pass this packed array into actually a routine that calculates the integral on the GPU. And it's the same way if you want to set things. You say, give me the topology, give me the data layout, give me the storage, give me what you want to do, and I will insert these values. Same thing. And if you look in like form Jacobian, we do it. We insert the element matrix after it comes back from the GPU. And all these functions are built upon a function for the transitive closure. It returns points and orientations. So, simple example. Suppose I have this 2-element thingy. What happens? Well, suppose I have a P2, P1 discretization. So the closure of a cell is the face, the 3 edges, 3 vertices, right? OK. If it's P2, P1, I have values on the edges for the velocity, values on the vertices for the velocity and pressure, right? Now, that's a kind of annoying way to get that data because velocity and pressure are mixed up. So the way that, in example 62, the way you actually get the data is I reorder so that all of the velocities are before all the pressures. And then you can separately deal with the fields. And no matter how many fields you have, and no matter what discretization, I can always do this reordering. And this is, I think, much easier to deal with. That way you can have separate physics functions for each field if you want. I said that there was a simple set of operations that enabled this. Here they are. Basically, you have one direction which says, what are my subcomponents? So if I have an edge, I can get the endpoints. If I have a cell, I can get the faces. If I have face, I can get the edges. And I can do the opposite. I can go backwards. I can have the transitive closure of that particular relation. And these are, I can have the meet and join, which is a typical thing for posets. So for instance, if I want to know what are the shared elements in common in the graph. So I might have one face and another face that share an edge. That would be the meet. And the join goes the other direction from the meet. So you might ask a question like, what do these set of vertices contain a cell? Yes or no? This is the entire interface for unstructured grids. And it can do anything that you want, I think. And this is what I normally show. So you can get a feel for what the talk was before we talked about unstructured grids. It was a list of vector operations. And I just want to show you that at the lowest level, PETSc makes it easy to interact with legacy code. So suppose you have this. I have legacy code. I would like to use this, but I don't want to go ripping up all my code. Okay, fine. I have a bunch of arrays, and I like them to be seen as vectors. Okay, this is what this interface is for. You can do it in C. You can create an array of a certain create a vector of a certain local size and get the array out, right? With getArray. You can do it in C. You can do it in Fortran 77 if you like pain. You can do it in Fortran 90, which I think is much more acceptable. And you can do it in Python. And you can do it at a higher level of abstraction. So suppose that instead of just a vector where you get this array out, suppose you tell me that you have a structured grid. Great. If I know you have a structured grid, I can give you an array that looks like a structured grid. Here, 2D. If it's 3D, you know, it would be 3 stars. And we allow you to do stuff. So we try to make it as easy as possible to write serial seaming code that we do the parallelism for. Okay, so we can easily construct a code to test your ideas. I mean, that's the whole point. If you can't write a piece of code in a week, something's really wrong. Something's not going right. So we have lots of debugging tools, lots of code management tools. We can take your existing code that runs pretty well, that solves a physical problem, and we can make it run faster and run bigger. Okay, and that's one of the things that we do really well. So for instance, suppose you have a serial code and you want to say, wow, I want to solve bigger problems. We can allow you to transplant almost wholesale your serial residual evaluation and use it in a parallel code. We can change your algorithm. So for instance, you say, well, I got a Stokes problem. Sometimes it gets hard, right? Or even I got a Poisson problem. Sometimes with the coefficient it gets hard. Great. We can do domain decomposition and field split and algebraic multigrid or geometric multigrid, and we can help you solve that faster. And look, I think we have one of the most portable pieces of software. I don't know of a place that we cannot run. We can run on your iPhone. We can run on Carver. We can run on any machine that exists, as far as I know. So if you want to write one code and have it be able to run anywhere on any machine and scale up pretty well, I think this is the option. So for instance, if you're going to spend your time, are you going to spend your time writing a MATLAB thing and then have it go nowhere when you exhaust the memory on your machine and have to completely rewrite? The Python version of PETSc looks almost like MATLAB. You can sit there and write 10 lines of code and have it work and have it scale. We have written a Python program that ran on 50,000 cores of Shaheen at KAUST, and it got excellent scaling. Now, look, Python execution is not fast. It's not. But what is your metric? If your metric is time to solution, time I spent writing and debugging my code, plus time I spent running, if you write it in a day and it takes a day to run on Shaheen, you're ahead. Okay? So consider how you do, what is your scientific process? How do you develop? How do you test? How do you write papers? And I think that we support a lot of different modalities for getting that scientific answer. And that's what I care about most, is getting the scientific answer. Okay, so I think I'm done. Yeah, we can take a break. I talk faster than I thought. But.
Are there any questions?
Oh yeah, I should. Yeah, go ahead.
Can you use the mic?
Say it again.
Do you support user elements or user material within this?
Okay,
this
so
structure?
like, are you saying user finite elements? You mean?
Yes.
Okay, so here's how I would support a user finite element. I would want a header. So suppose you were trying to use example 62. What I would want is I need a header like this guy. And what does this guy contain? This guy is generated by fiat, by the way. So I actually have an example. So there's a very smart guy at Texas. His name is Todd Arbogast, and his student, Avi, is working on a new element for Darcy-Stokes. So Darcy-Stokes is where I have a incompressible fluid and a deforming solid matrix, okay? So the problem here is that I need to control not only the divergence residual of the fluid, but I need to control the elastic residual of the solid. Okay, and so normal finite elements don't do a very good job of this. Lagrangian is total crap, actually, for the solid. So what they have is they had their own finite element that they came up with. And they said, well, how do we put it in this framework? And so what you do is you say, well, I would like the, so for quadrature, I have the quadrature points, which is just, x, y, z, or whatever, or x, y, and weights. And then I have the basis functions. Now, what is that? It's the evaluation of the basis function at the quadrature point. So if it's function k at quadrature point q, I want that. Okay? If you give me this, if you want to be able to do Newton, you need this. So you need the evaluation of the basis function and its derivative in a certain direction, in a certain direction, d, at the quadrature point. If you can provide this, we can do it. And that's why we can do, it's no different for us to do conforming elements like Lagrange or non-conforming like RT or BDM because we adopt this breakdown. This is Rob Kirby's idea, I have to say. But it works great. And this is what we're trying to expand to finite volume. Finite volume, if done with a pointwise Riemann solver, and if you, there's a good paper by Kyle Manley and Andy Terrell called about mini-claw, which is a pointwise Riemann solver. If you do that, then you have the same kind of formulation as you do for finite element quadrature. You have physics functions that hold. So for instance, in example 62, if you look, what we do is we say, okay, we have a test function and a function of the fields and their gradients. And then we have a gradient of a test function and a vector function of the thing. And so for instance, Laplace, that's just this. So you get grad V, grad U, what everyone recognizes as Laplace. Everything that is doable in first order is writable like this. So the user writes a pointwise function where they get point. So if I wrote this in quadrature form, right, it would be sum over quadrature points, quadrature weight, and then F1 of the values at the quadrature points, and then the differentiation matrix, right? This is assembly onto the element where I sum over the weights and weight them. Okay, so if you adopt this kind of formalism, you can do all the finite elements. But I think you can also do finite volumes in the same way because you have reconstruction here, basis functions, right? Where you're reconstructing the value on the cell. And so that's what we're trying to do right now. It's not done. But example 62 should work for any user element, like you're saying, if you provide this header. And this header is what I showed in the beginning, is what's generated by that small piece of Python. And in the hands-on, I'll run it. And in the slides, I showed a lot of different, strings of options that you can construct different solvers for it, like, these field split solvers. So you'd be able to, if you gave this header, you'd be able to do field split with whatever element you wanted. Yeah.
Another question. Can I skip the assembly and directly give the global stiffness matrix?
Oh, yes. Okay, so there is a let's see. What you want to do is, I thought I had it in here, is you want to do form function instead of form function local. Yeah, I do. Okay, so what's happening here? So what I say is, oh, I'd like the DM to handle the assembly of my thing, and then I'll just calculate the local part. Okay, that is easier for a lot of people because they want to think serially and then have me do the assembly. You don't have to do that. You can just say, here's a function, I give you the thing. Don't listen to anyone else. And then you would just change this from SNES DM compute Jacobian to my Jacobian, and you give me everything. No problem. I think this is a crucial point in the design of interfaces. One monolithic interface doesn't work. You need to have multiple entry points depending on what the user wants to do. And we try very hard to have multiple entry points depending on what you want to do. And so if you want to provide me the full parallel matrix, go ahead. If you want to provide me with a serial part of the matrix that needs to be assembled, I can handle that too. Yes?
So there's, I remember somewhere in the PETSc user manual fairly early on, it says something to the effect of, don't use PETSc if all you want to do it, if all you want is the linear solvers out of it.
Yeah, I mean, well, I guess I'll go a little farther. So, I mean, that's Barry, and he likes to discourage users because we have to support them. But I think what he's going after is the following. If all you want to do is just replicate your linear solver, it's not very useful. The useful part of PETSc is trying new things. That is what our whole aim is. So originally PETSc was written so Barry and Bill could write a book. It's a very good book, actually, Domain Decomposition Methods. If you want to understand domain decomposition, you should read it. But they wrote it so they could do tests, because at the time, you either solved this way with MinRes, or that way with GMRes, or that way with BiCG, and that's how it was. And so they said, well, we want to write a package where we can test all of them at once. Well, hopefully our horizons have expanded, because what I want to do is say, well, how does P2 compare to P1? And how does P2, P1 disk compare to P3? And I want to say, how does a segregated KKT smoother on geometric multigrid compared to algebraic multigrid on a block composed multiplicatively with a geometric multigrid on the temperature? And I can do all that from the command line. And so that is the point. It's trying things. And the reason you want to try things, it's not a trivial reason. The reason is that you cannot understand what will work. It's a very difficult thing in science to say that something is not knowable. And people really believe if they work hard enough, if they read enough papers, that they will be able to figure out what solver is best. But I'll tell you the truth, it's not possible. And there are several negative results to this effect. And so the best thing to do is write in a flexible way so that you can try everything. And it's a tough engineering kind of result, I understand, but it's the way that the world works right now. I guess I will tell you what, we have some time, so I want to tell you guys something about modern architectures. So PETSc can run on the GPU, and we have been incredibly frustrated by the large number of people knowing nothing trying to run on the GPU. And so I would like to tell you when it will be useful to run on the GPU and how these things work. So GPUs are essentially stripped down processors, okay? And there's an absolutely beautiful, mind-bogglingly beautiful talk by this guy, Phaleon at Stanford, that you can Google, and I'll give you the address, about how you would get to the GPU. If you decided that, you know, oh, I'd really like to compute faster, what would I do? Well, I'd put more cores on. Well, okay, I put more cores on, but I'm spending a lot of time in instruction decode and stuff like that, so I'll vectorize. That's the whole motivation for vector computing. Is I'd like to take all of these instructions that I'm executing in parallel, and I'd like to reduce the complexity. So okay, so all these are going to march in lockstep. Then they're going to do the same instruction. Okay, fine. That's vector computing. Then you're like, well, I'd also like to get rid of a lot of the complexity of cache snooping and all this stuff. Okay, so what we're going to do, we're going to have one shared local memory for all of the vector units. Okay, we're going to do that. I don't want to worry about, you know, coordinating between different vector units. Okay, so what I'm going to do is I'm going to make the cache totally user-controlled. So you declare what goes in this, and now I'm going to call it shared memory. Okay, so I have a vector unit with some shared memory. Now we're back to 1980 when the Cedar project at UIUC was designed, and that's exactly what they had. A vector unit with some shared memory and some global memory, and that's a GPU. Why GPUs are important is because they made several design decisions that are important. They have a really wide bus. Why is this important? It's important for us because sparse matrix vector product, which is the workhorse of all Krylov methods and most other preconditioning methods, that is controlled by memory bandwidth. So is finite element assembly, so is dense matrix vector product. Okay. If you have a higher memory bandwidth, you can run faster. The memory bandwidth is higher on a GPU because of design decisions. It's higher because they have a really wide bus. It's impossible to get one element from memory. You have to get 8 floats, and you have to get 16 floats on the Fermi. If you don't use all of these, they fall on the floor and you get really bad performance. And this is what is known as coalescing. What it means is that coalescing is using all of the memory that I ask for every time. That's what it means. I was really upset when I figured this out because I thought it was going to be a sophisticated thing, but it's not actually. Every time you go to memory, you get 8 floats. If you don't use all 8 floats, you get poor performance. So coalescing is using all 8 floats that I get back every time. That's it. And so the other less important part of GPUs is oversubscription. I divide all of my work into small pieces, and all the small pieces can run whenever they want. But that's done every day on all kinds of CPUs, so it's not as important. The important part is wide buses and vectorization, because you have a length 8 vector, which is pretty big. It's bigger than most multi-core processors, okay? So if you want to understand how to run fast on the GPU, vectorize your code, length 8 vectors or length 16, and understand how to use grouped memory accesses. The reason this is important is not because of GPUs. GPUs have a lot of drawbacks. Number one, they have the worst software support in the world, and it doesn't seem to be getting any better. The libraries available for GPUs are almost uniformly crap, and the way to use them is just horrible. And no matter how much you talk to these guys, they don't seem to do any better. However, any modern processor, so look at the Intel mic or anything that seems to be coming out, it has a wider bus and it has vectorization. And so any code that you write from now on, if you want a significant fraction of peak, will have to be vectorized, and it will have to accommodate a wider bus. So learning to program for GPUs is instructive for that reason, is that you will learn to program for any modern architecture. And so it's difficult for people to talk about GPUs because you have this intrinsic rejection because the support is so bad and the libraries are so bad and you just don't want to tell people to use them. But on the other hand, this is computing. This is the future of computing. And so it's important to recognize what it has in it. So if you configure PETSc with the options that I showed you in the talk, you can try the GPU, which probably exists in your laptop, and see how it performs. My laptop gets about a factor of 2 on a sparse matrix vector product, and a good card like a GTX 285, which was a good card in 2008, gets about a factor of 4. But you're not going to do any better than that. These factors of 100 are just ludicrous, and they don't shed any glory on the people that popularize them. So, you know, that's my GPU spiel. So I don't know if anyone's going to say any more about that.
So I guess this afternoon you're going to show some examples on.
Yeah, the hands-on, I'll run all the EX62 examples. I mean, the important point is that now we have a consistent framework for dynamically constructing preconditioners for multiphysics problems. We didn't have it before. And this is very important because, additive Schwartz method, which is what most people throw at something parallel, does not work on these things. And we knew it for years because people would tell us Stokes is very slow. Now we have a legitimate, parallel, scalable way to solve constrained problems. And we also, and that's why we're able to do things with this SNES VI. We're able to solve variational inequalities because we have this. So in the hands-on, what I'll do is show you an example of solving isoviscous Stokes. I know isoviscous Stokes is not amazing anyone, but it is the simplest problem for which you get a saddle point and can physically understand the results. And if you have constraints in your problem, we can likely apply the same methodology. So for instance, this is a problem that we apply exactly the same methodology to a very interesting problem in dynamic rupture. So we can put we have a cohesive cell formulation for fault rupture that we can put any kind of rheology. So for instance, we have I think the hardest one is this rate and state friction that we can put on this, and we can scalably solve rate and state friction problems.
Is field split the method that you talk about, or is that what you encourage people to?
Yeah, I encourage anything with a saddle point. You would do that, and I'll run it in front of you. And actually, what would be better is you run it in front of me, and these really work. Let's see, I have those. Yeah, like this is a pretty decent preconditioner actually. So if you run this, it should work. And actually if we give like map view, it'll show you the matrix and stuff like that.
You mentioned that LibMesh
I shouldn't be too hard on those guys. So I don't know whether they support it or not. The last release didn't, okay? But it should. And they're pretty good about updating. So hopefully this next release will get everything right.
I've been using Moose.
Oh, I totally know Moose. Yeah, yeah. In fact, Jed is in Idaho, right? That's why he's not here. So Moose definitely uses all of the field split stuff. Yeah, so it's doing the right thing. Yeah, since he brought it up, Moose is very interesting. So that's a multi-physics framework. It's quite flexible. It's much more flexible than what I was talking about. So you can run Monte Carlos for some of the underlying physics and all sorts of goofy stuff like that, and it will still work. And it's very neat, and it has a lot of tests. So I would encourage you, if you're doing, you know, it has contact and a lot of neat stuff. So if you're doing solid, you know, kind of structured problems that you might consider LS, Dyna, or something like that, consider using Moose. Okay, it's fine.
You know, the reason is that you're going to discuss the, you know, the operator, the metrics. Just because, you know, for performance issues, something that I found that people have a lot of trouble is understanding the pre-allocation.
Okay. I should have said it. I thought it was in my slides, but maybe I glossed over it. So one of the #1 ways that you can screw up performance is not pre-allocating the matrix layout if you use a matrix. There are lots and lots and lots of good reasons to never use a matrix. And Jed has a great slide showing that the performance of matrix-free codes is just far and away better than codes with a matrix. But sometimes there's no alternative because you don't know how to precondition things without the matrix there. So if you have a matrix, it should be pre-allocated. My approach to this is to use dm get matrix, which will give you a matrix that is properly pre-allocated. Now, that means you have to use a DM. So you have to tell us something about your geometry and topology. If you don't want to, you can pre-allocate your matrix by yourself. You can say, look, this is how many entries are in every row of my matrix. You know, usually it's easier to tell us, I have a structured grid, I have an unstructured grid, whatever, here's how it looks. And we can do it for you in parallel. So, yeah, I should have said that. That is how most people clear up the first order performance problem, is to get their matrix pre-allocated correctly. All right, I think we're all set.
So let's thank Frank.